Problem is 3.23 part B. Here we have a cantilever beam which has this load W acting here at a distance A, and the total length of the beam is L. We have to draw the shear force bending moment diagram using singularity function. So if you look at the support here, this is a cantilever beam, so there will be a reaction here, and which will be equal to this force W, and there will be this moment here balancing the moment coming from that W force. So the value for this is minus WA. Now when we write singularity functions here, there will be two functions that will be useful. We have a point load and we have point moment in this case. So a point load we will use x minus a minus 1, and for moment we will use x minus a minus 2. Now when you integrate this, first integration will give you 0. Similarly here, first integration will give you minus 1. And when you integrate it one more time, this 0 will become 1, and in this case it will become 0. Okay, now this is after integration, and this one is also integration. So let's start writing the intensity function qx for this here. Let's start from the reference side. First we have a point moment, so minus WA, it's acting at 0, so x minus 0, it's a point moment, that's why minus 2. Then we have a positive force W, since it's a point force, it's going to come with minus 1, x minus 0 because it is acting at x equals to 0. Third one is this one here, it's a negative force, so minus W, x minus acting at a point force, that's why minus 1. So this is your intensity function. Now from intensity to your shear force, we can get this by integrating this with a negative sign. So if I integrate this, because of this negative sign, we can flip all the values, so this becomes plus WA, x minus 0, minus 2 integration gives you minus 1, minus W, x minus 0, minus 1 integration will give you 0, plus W, x minus a, minus 1 will become 0. Similarly, if I integrate it one more time, from here to here, I will get the value of bending moment, so minus V dx. So if I integrate again, so signs will flip again, this x minus 0 minus 1 will become 0, sign will flip here again, x minus 0, 0 becomes 1, minus W here, x minus a, 0 becomes 1. So after we get these functions, we can evaluate this in different segments. So now we can divide this beam into two segments. One is x less than equals to a, and the second one is x greater than equals to a. So if you focus on segment number 1, so segment 1 here, which is x less than equals to a. For this segment, your x minus 0 will give you positive value, but x minus a will give you a negative value. So this is the only function that we can consider here. So if I write my v1, I will evaluate this function right here and this one right here. So what do I get from here? I get WA x minus 0 minus 1 minus W x minus 0 to the power 0 from here will become 1, so this remains W. Now there is a problem here, that if you look at this function, this is your unit impulse function, and this will give you an infinite value at x equals to 0. So what does this mean? This means that your v1 is undefined at x equals to 0. Everywhere else the value is going to be minus W for this. Similarly, if you calculate your MB1, for MB1 also we are going to calculate this and this one. So first term gives you minus WA, x minus 0 to the power 0 will give you 1, so we have minus WA there, plus W. From this part, x minus 0 to the power 1 will give you x, so we get WX. So if I simplify this, I can write this as W common x minus a. So this is your moment. Now we focus on segment number 2. So your segment number 2 for the beam is when your x is greater than equals to a. For x greater than equals to a, both of these values, x minus 0 will also give you positive and x minus a will also give you positive. So this means that all three terms here, this one and this one, all of these three will be considered for your segment number 2 calculation. Okay, so if you notice, the first term here and the second term here is already calculated in your v1 and mb1. So when we write your v2, we can directly write that v2 is equals to v1, which is bringing first two terms, and to that we can add this last term right here, so plus W x minus a to 0. So this will give us v1 value is minus W for us, and from here we are going to get plus W, so your B2 value becomes 0. Similarly, if you look at your MB2 is going to be MB1, which is first two terms, this one, and we can add the last term here, which is minus W x minus A to the power 1. So if you simplify, put the value of MB1, which is this one right here, so W x minus A minus W, if I write this as a polynomial, this becomes x minus A. It cancels out with this, so you get 0 here. So now we have four values. Your V1 is equals to minus W except for x equals to 0. Your MB1 is equals to W times x minus A. Your V2 and MB2 both are equals to 0. So we can plot these values. So let me draw one axis here. So there are two segments. First one is x less than equals to A, and second one is x greater than equals to A. So here we are going to plot V1 and MB1. So your V1 value is minus W. So this will become the constant line right here. Your V2 value is equals to 0. So in this segment we can plot a constant line of 0. So this is how your shear force is going to look. And remember, at x equals to 0 we had undefined. So this is where your shear force is going to be infinite. So we can shade this region. This is how your shear force diagram looks for this beam. Now when we look at your bending moment, your MB1 is given by this equation. So we can evaluate this at 2 points, x equals to 0 and x equals to A. At x equals to 0 we get minus WA, at x equals to A we get 0. So maybe we start from here, and this value right here is minus WA, this one right here is 0. Connect them by a straight line. Your MB2 value here is 0, so we maintain a constant 0 there. So we can shade this part. This is your bending moment diagram. Now for completeness, we can draw the convention that we are following. So this is for bending moment, this one is for the shear force. So let's mark plus sign. This is how your shear force is drawn, and this is how your bending moment is drawn.